And so we left off with this fractional precipitation example. And in the fractional precipitation, the example I gave was trying to separate the 3+ cations, iron 3+, chromium 3+, and aluminum 3+, from the 2+ cations. The 2+ were, what was it, calcium 2+, magnesium 2+, etc. And the reason this fractional precipitation works is because these are less soluble hydroxides. And these are more soluble hydroxides. But all of these are insoluble hydroxides. It's just that they're degrees to insolubility. And so if that's the case, then the fractional precipitation strategy works. So in this particular fractional precipitation, what we want to do is we want to start precipitating out the +3 ions. And the one that precipitates first will be the least soluble of these. I can't remember which one was the least soluble. We would look that up in the KSP table here. Let's take a quick look at the KSP table here. And we're comparing the iron 3. Actually, let's look at the aluminum first. Aluminum hydroxide is 10 to the minus 33. Now, the only way we can compare the KSPs directly is if the solids split up into the same ratio of ions. That is, 1 aluminum hydroxide breaks into 1 aluminum and 3 hydroxides. Well, the same thing happens with chromium and iron. So let's take a look at chromium. So that was 10 to the minus 33. If we go to chromium 3 hydroxide, it's 10 to the minus 16. It's going to split up into 4 ions. 1 chromium 3 hydroxide splits up into 1 chromium and 3 hydroxide, so a total of 4. So it splits up the same. And therefore we can compare the KSPs directly. This is 10 to the minus 16, that's 10 to the minus 33. So there's a huge difference. 10 to the minus 33 is much smaller, making it much less soluble. And so iron will precipitate out first. And then which one would precipitate, not iron, aluminum, sorry. Aluminum would precipitate out first when compared to chromium here. But what about iron? So let's go down to iron. If I look at iron 3 hydroxide, it's 10 to the minus 38. So we have 10 to the minus 38, 10 to the minus 33, 10 to the minus 16. So iron 3 hydroxide will precipitate out first, correct? Because it's the least soluble of these. Followed by aluminum, and the most soluble would be the chromium. And so the chromium would precipitate out last. So maybe I was wrong in my strategy for this. So iron precipitates first, followed by aluminum, and then chromium. And so what I want to do is I just want to slowly precipitate out the iron, and then eventually both iron and chromium precipitate, and eventually iron, chromium, and aluminum precipitate. Because to completely precipitate it out, that is to get all of it out, would require an infinite amount of hydroxide, which we aren't going to do. Therefore, we have a criteria, it's somewhat arbitrary criteria, and the arbitrary criteria is what? It's 99.9% precipitation. It's going to be complete enough. But all these will continue to precipitate as we add more hydroxide. And so the chromium precipitates out last, and what we want to do is we want to precipitate out all the chromium before the least soluble one of the 2+ ones begins to precipitate out. And so we'll take a look at how much chromium precipitates out before any of these precipitate out. And to determine that, like for example, if you want chromium to begin precipitating, in order for chromium to begin precipitating, what we do is we don't calculate the solubilities. In a fractional precipitation problem like this, you don't want to calculate the solubilities because the solubilities aren't necessary. Yeah, it's helpful to know, the least soluble ones will precipitate first, but what we want is we want to calculate the hydroxide minimum required for precipitation. So I'm going to skip calculating S entirely and just go to the hydroxide minimum required for precipitation. So I know chromium, how much hydroxide, that's going to require more hydroxide than iron and aluminum. Iron requires less hydroxide to precipitate, and that's why it precipitates first. Chromium is going to require the most hydroxide out of these three. And so how much hydroxide is required for chromium to begin precipitating? Well, we can calculate that based on the KSP equation. So the KSP equation for chromium is just going to be KSP divided by, well, in this case, the hydroxide minimum required is going to be KSP divided by the chromium concentration, to the 3 plus, and then we'll take the cube root of that. This is just to get it saturated. So for example, when the hydroxide is equal to this concentration, then the hydroxide and the chromium are at the max being KSP here. And so what we need to do is we need to change this from equals to greater than. And so that's what I'll do here. I'm going to change this from equals to greater than because we need more than the maximum. In other words, we need to supersaturate the solution. So if we have just the maximum, that's called a saturated solution. If we have less than the maximum, it's unsaturated. And so iron is going to require the least amount of hydroxide to saturate it, and then we exceed that and we'll start to precipitate out. And then followed by aluminum, eventually the hydroxide's got to increase, we'll hit enough to saturate aluminum, and then we go beyond that and aluminum will start to precipitate out. And then as we continue to increase the hydroxide, iron and aluminum are both precipitating, and then we'll hit this minimum for chromium. And once we exceed that minimum for chromium, then all three of these will continue to precipitate. And so what we need to do is we need to increase the amount of hydroxide for chromium to precipitate it out as much chromium as possible before we hit the 2 plus. And so what we need to do is we need to calculate the hydroxide minimum required to precipitate out the 2 plus, or we just see which one is the most, or not the most, the least soluble of these, and that's going to precipitate out first. And so we want to continue precipitating out the chromium until we hit the point at which one of these will begin to precipitate. And then we'll calculate that. And then we'll do an additional calculation to see what percentage of the chromium we removed. And it turns out that we can do a complete precipitation of the chromium before this precipitates out. And you just have to have the right hydroxide concentration. There's kind of a, 99.9% is hit well before you start to precipitate these. So we can continue increasing the hydroxide, and we're going to precipitate out more than 99.9%, and then we'll stop. And so there's kind of a range here where we can get complete precipitation, that is more than 99.9% precipitation. And that range is some hydroxide concentration. And that hydroxide concentration we can describe in terms of pH. And so what we're going to look at here is pH and solubility. Next, that's the next topic. So the way we accomplished this is we made a buffer solution. That is, we had ammonium's acid, and we added ammonia to this. So you have ammonium in there, and then you add ammonia, the pH increases, right? And then we add enough ammonia to turn red litmus paper blue. And then that's going to be around pH 7. So around pH 7 or so. I need to know for the indicator. We don't know what the indicator in litmus is, but it's close to 7, let's say. So around pH 7, we'll stop that. And so this was making the buffer to get the pH right, and then we have the right hydroxide concentration roughly. This doesn't have to be too precise because we have some wiggle room there in our qualitative analysis. But what we're going to do is we're going to look at pH and solubility more quantitatively here. And so let's take a look at the 2+ cations here and see. What were our 2+ cations? We had magnesium, calcium. Do we have barium? Was barium one of them?
The qualitative analysis?
Yeah, in the qualitative analysis. Magnesium, calcium. Well, I can't remember. So what we're going to do is we're going to look at different problems. So for example, one problem we can consider is at what pH will chromium begin to precipitate? Actually, chromium was least soluble, yeah. What pH will chromium begin to precipitate? So what we're going to do is we're going to calculate the hydroxide required to saturate the solution. So when we're doing chromium, actually, let me take a step back. When we're dealing with solubility, we always use the KSP equation. So in terms of solubility, precipitation, etc., that is, solubility is like dissolution or dissolving. In precipitation, we look at the KSP equation. The KSP equation is always the same. It's written as a dissolution or dissolving. So we're going to dissolve chromium 3 hydroxide. Well, chromium 3 hydroxide is an ionic solid. Excuse me. So it should break up into the ions, chromium 3 and 3 hydroxides. Hydroxides here. And so we should generate the KSP expression. The KSP expression is going to be the chromium 3+ concentration times the hydroxide concentration cubed. Chromium 3 hydroxide solid has an activity of 1, so this is just divided by 1. And so when we calculate the hydroxide minimum, you know, it's going to be greater than the KSP divided by the chromium concentration to the 1/3. Now, at what pH will the chromium 3+ begin to precipitate depends on how much chromium 3+ is in there, you know. The more chromium 3+ that's present in here, the less hydroxide we'll need in order to precipitate. The less chromium 3, the more hydroxide we'll need. And so we need to know what is the initial concentration of the chromium 3+. At what pH will the chromium 3+ begin to precipitate? And so we're going to assume that we have 0.1 molar chromium 3+ here present. And again, the more chromium 3+, the less hydroxide we need. And so we'll just plug this in. So the hydroxide minimum will be greater than the KSP. What was the KSP again? So let's take a look at the KSP. Two times 10 to the negative 16. Oh, this is so small. 2 times 10 to the negative 16. There. 2 times 10 to the negative 16 divided by the chromium concentration, 0.1 to the 1/3. All right, actually, I'm using my phone to record this, so I can't use it as a calculator. Can someone calculate this for me? This is a calculation I skipped in the morning, but I'll do this afternoon. Does somebody have it?
I got 1.2599.
1.2599
times 10 to the negative
times 10 to the negative 5 molar hydroxide. So what this means is if we get this concentration, we've saturated. We have to go bigger than this. We need more hydroxide to begin to precipitate. If we're under this concentration, it's unsaturated. Okay, so the way it's going to work is if it's equal to this concentration, then we call it saturated. If it's greater than this concentration, we call it supersaturated, and we're going to get a precipitate. If it's under this concentration, it's called unsaturated, and there's no precipitate that's going to form. And so this is the minimum, because if we go under this, it's going to be unsaturated. We need to go over this so it becomes supersaturated, and so this is why I have greater than over here. We need more than this. Well, if we have this, that's the hydroxide. What is the POH? Can somebody take the negative log of that? $1.899?
4.899.
4.899? Thanks. Okay, is this the POH maximum or is this the POH minimum? Because hydroxide concentration and the power of the hydroxide have an inverse relationship. This is the POH max. We do not want to exceed this. We want to go below this POH. Which means, what is our pH?
$9.10034.
9.10034. This is going to be what we call our pH minimum. So our buffer solution was higher than 7. And so what this means is we can't go below this pH. If we go below this pH, there's not enough hydroxide to precipitate. We need to go above this pH to have enough hydroxide to precipitate out the chromium. Okay. So that's one example of a pH insolubility calculation. Let's take a look at some other examples here. Next. look at this one I did this morning here. All right, when we look at pH and solubility, we're going to introduce a new method. And so this is just iron 3 hydroxide. Iron 3 hydroxide, well, it's a hydroxide, so pH is going to have an impact. As the pH goes up or down, the hydronium goes down or up, which means the hydroxide is going to go up or down. And so as the hydroxide concentration goes up or down, that shifts it. We could shift it to the left or we could shift it to the right. In this particular example, if I increase the pH here, that's going to increase the hydroxide. If I increase the hydroxide, that's going to shift it to the left. If I shift this to the left, what the end result is going to be less soluble. I'm going to have more precipitation happening here. When we look at pH and solubility, I'm going to introduce a new method here, and this is called the combined method. We didn't talk about the combined method yet. We just talked about simultaneous. Simultaneous was too much, the math, and therefore we tried to simplify it using stepwise, as long as certain assumptions are correct and stepwise works. You don't have to solve it simultaneously. And so, that's pretty much it, either simultaneous or stepwise, but now we're going to have a third method, the combined method. Why didn't I talk about the combined method before? I didn't talk about the combined method before because it has very limited application. One application you might think of for the combined method would be phosphoric acid. Phosphoric acid is a bit of a pain. Because phosphoric acid is a triprotic acid. And so let's say I want the pH of phosphoric acid in water. If I want the pH of phosphoric acid in water, I have to deal with Ka1, which is just taking phosphoric acid and water and making hydronium and dihydrogen phosphate. But I still have 2 hydrogens left on dihydrogen phosphate, 2 acidic hydrogens. So Ka2 would be the second hydrogen here. Dihydrogen phosphate plus water yields hydronium and monohydrogen phosphate, that's Ka2. But I also have Ka3, which is monohydrogen phosphate, hydrolyzing water to form hydronium and phosphate. And so I have these. This would be step 1, step 2, step 3, and then I have a step 4 potentially, which would be Kw. And so that's 4 ice tables. Well, maybe I could get rid of 3 of the ice tables. One way to get rid of the 3 of the ice tables is to combine these 3. That is, I'm going to combine Ka1, Ka2, and K3. If I do that, then I'm going to have phosphoric acid, and dihydrogen phosphates cancel, monohydrogen phosphates cancel, so I end up with phosphoric acid plus 3 waters gives me 3 hydroniums and a phosphate. And then you go, I took 3 ice tables and combined it into 1 ice table. Isn't that a tremendous time saving? Yeah, that's a tremendous time saving, but it fails. Why does it fail? Well, it doesn't fail because K, I can easily calculate the K value for this. What is K value for the combined? The K value for the combined, that is the net reaction, is Ka1 times Ka2 times Ka3. So this is easy enough to calculate. Now, the problem with this is this. When I look at the combined or the net reaction here, there are some species missing. The species missing are dihydrogen phosphate. It canceled here. Does that mean dihydrogen phosphate does not exist in solution? No. When we inventory this, the major species are this. When we inventory, the major species are going to be H3PO4 molecules, followed by hydronium, followed by dihydrogen phosphate. Dihydrogen phosphate is the third most abundant species in an equilibrium mixture here of phosphoric acid and water, but when we look at the combined equation, there's no dihydrogen phosphate present here. So that one, which is the third most abundant species we'd expect, is completely gone from the equilibrium. That's a fail. The other reason it fails is monohydrogen phosphate. Monohydrogen phosphate would be the fourth most abundant. And then the fifth most abundant would be phosphate. And so when you look at this, it looks like phosphate is one of the most abundant species. No, when we actually do the inventory, that is when we go through step 1, step 2, step 3, and step 4, we'll see that phosphate concentration is actually very small. Not so big. We get a small phosphate concentration here because of the K net, but we're missing species that are more abundant, which would be dihydrogen phosphate and monohydrogen phosphate. And since those species are more abundant, they're completely missing here, and therefore this is not really showing the complete equilibrium present here. So we didn't use the combined method. We had to break this down into individual steps to make sure we didn't lose or accidentally lose any species here. So since we're missing dihydrogen and monohydrogen phosphates, these are relatively major species in H3PO4 equilibria, it's a failure. So unfortunately, we can't use the combined, and this is why we didn't do the combined method here. In Chem 1A, you could do the combined because oftentimes you don't really care about the intermediate or those other species. Those aren't intermediate species, the other species present in equilibrium. However, the combined method does work for a limited number of scenarios. The problems still exist, but it's like simultaneous and stepwise. We really should do it simultaneous, but there's such a small perturbation of the previous step, we don't really worry about it. Well, in this particular case, we don't really worry about it. So if we take a look at iron 3 hydroxide, and what we're going to do is we're going to look at how pH directly affects this. Well, like in the Henderson-Hasselbalch, you could do the Henderson-Hasselbalch either in terms of pH, or you could do the Henderson-Hasselbalch in terms of pOH. In other words, we could describe, when we have a HH buffer, we can either use the Ka equation for the acid component of the buffer, or we could use the Kb equation for the base component because they describe the same equilibrium. One just describes it in terms of hydronium, the other describes it in terms of hydroxide, but they're tied together. Well, the same thing here. I can just leave this in terms of pOH, But sometimes I don't want to leave it in terms of pOH. I'd rather have it in terms of pH. In terms of pH, pH is acid. Acid would be hydronium. And so in terms of acid, I want to introduce acid into this equilibrium. If I introduce acid, then acid is going to attack the strongest base present in the equilibrium. And so if I look at the strongest base out of these three will be hydroxide. And so the strongest acid, hydronium, will attack the strongest base, hydroxide. And since we have 3 hydroxides here, I'm going to keep it balanced here. This is not combined, this is just keeping it balanced. So 3 hydroniums plus 3 hydroxides is going to yield 6 waters. Now normally, if I have hydronium and hydroxide, hydronium is a strong acid, hydroxide is a strong base. So if I have a strong acid, strong base, what's my K? Is it very large, very, very large, or very, very, very large? Very, very, very large. That's my K. So if I combine these two equations, I run into a problem because if I want the combined equations K value for the K net, the K net value I can't use very, very, very large. And so in all the previous chapters, we're going to do that. We're going to use, very large, very, very large, or very, very, very large. But in this particular chapter, when we do the combined method, we don't do that. And so what we're going to do is we're going to look at this equation. This is strong acid, strong base, but we're going to look at the reverse equation. If we reverse this equation, what is it? It's H2O goes to hydronium and hydroxide. In other words, it's water autoionization. In other words, it's Kw. So if I look at the reverse equation, it's Kw, but it's multiplied by 3. So it's 3 times Kw, but we don't do 3 times Kw. If I triple the reaction here, I have to cube the K here. So this is actually 1 over Kw cubed. Do you see that? The reverse. Well, then why don't I use that for all my, you could, but you know, when we use very large, very, very large, and very, very, very large, do you know what we're doing? We're resetting the equilibrium. Whenever we use one of those, we have to reset the equilibrium all the way to the right. And then we go on to subsequent steps, and the subsequent steps will tend to correct that. And so it's one way of getting students to reset the equilibrium. But here, what we're going to do is we're just going to combine these, and we're going to get something called KSP with acid. And so here I have my KSP, and then I'm going to add my acid, and I'm going to get something called KSPA. KSPA is going to tell us the hydronium or the acid dependence on KSP or the pH dependence on KSP. Now, we're missing a species. When we combine the equations, what major species are we missing now? What species in this equilibrium, the KSP equilibrium, is gone in the combined? Do you see hydroxide in the combined? No. So does that mean the combined method fails? And it turns out the combined method does not fail here. The reason the combined method does not fail is because hydroxide and hydronium have a seesaw relationship. So if the hydroxide goes up, the hydronium must go down, and vice versa. And so they're tied together. And so I could either describe this equilibrium in terms of hydroxide, or I could describe this equilibrium in terms of hydronium. It doesn't matter. And so for pH, I'd like to describe things in terms of hydronium. That's why Henderson-Hasselbalch, for the Henderson-Hasselbalch, we only use the pH version rather than the pOH version. The pOH version will give you the same answer, you know. But it's just easier just to use the pH version because, yeah, I mean, if we lived in the pOH universe, I guess the pOH version would be better, but since everybody describes things in terms of pH rather than pOH, we might as well just use the pH version. It does have certain implications for this simplifying assumption. I mean, if we throw everything in the pH version of the Henderson-Hasselbalch, then sometimes it gives the appearance that the simplifying assumption fails when in reality it didn't fail. So this tells us directly how this is going to be impacted here by the hydronium. So we just have one ice table to solve here. Now, when we're doing these calculations, we have to worry. Let me see, I talked about it. Is the pH, is that the initial pH, you know, or is that the final pH, or is that the pH throughout? I mean, pH, because we have buffers, the hydronium concentration could stay relatively constant. If this were a buffered solution, then the initial and the equilibrium and the change should, there's going to be a change. So let's say I'm going forward in this reaction, I'm losing hydronium. In a buffer solution, if you lose hydronium, the buffer shifts its equilibrium to produce more hydronium, therefore maintaining a stable pH. And so the initial hydronium and the final hydronium should be the same in a buffered solution. However, if it's an unbuffered solution, then the initial hydronium will be different than the final hydronium, therefore the initial pH and the final pH will be different. And so when people are asking about pH and solubility, you know, is it buffered? Or is that the initial pH, or is that the final pH? You have to read the question carefully to determine what they're talking about. So something like iron 3 hydroxide, it's easy to see that pH is going to have a significant impact on the solubility. In fact, for this, the more hydronium, the lower the pH. The lower the pH, the more this shifts to the right, or the more this shifts to the left. So if I increase the hydronium and lower the pH, this is going to shift it to the right, which is going to make iron 3 hydroxide more soluble. And so it turns out that iron 3 hydroxide is very insoluble in water, but extremely soluble in acid. You know, all we do is add a bunch of acid there, shift this to the right, and we can completely dissolve the iron 3 hydroxide. You did this with aluminum. Aluminum is extremely insoluble, and so aluminum hydroxide is so easy to dissolve. Just add acid, shifts it to the right, and the solubility goes up. And so the solubility changes depending on pH. You know, for these, the lower the pH, the more soluble. The higher the pH, the less soluble. And it's just shifting this via Le Chatelier's principle. We're going to calculate the solubility in a minute. But not everything has hydroxide. Is hydroxide the only strong base around? Are there other strong bases? Yeah, there are other strong bases. So for example, this one, manganese 2 sulfide. Manganese 2 sulfide, when we look at the KSP equation, it should break up into manganese 2 ions and sulfide ions. But there's a problem with sulfide ions, and one of the chemical properties of sulfide is that it is a strong base. And what do strong bases do in water? Yeah, they hydrolyze water completely. And so immediately when we form sulfide, it's going to hydrolyze water. When sulfide hydrolyzes water, what forms? Well, sulfide is going to pluck a hydrogen off water, and it's going to form HS minus, and water is going to lose that proton and form OH minus. So strong bases hydrolyze water completely. So this is going to be very large. Sulfide plus water, you know, strong base plus water gives a KB that is very large. Well, the KB is very large, but when we do the combined method, we don't want very large. You know, we want an actual number for this. Do we have an actual number? Actually, we don't have a number for this particular one. We don't have a number, but it's going to happen immediately, and we can't prevent it from happening. Therefore, free sulfide doesn't exist. Free sulfide doesn't exist, so we're going to use the combined method here. There's so little free sulfide, it's negligible, because that sulfide is immediately going to attack water. And so by combining these two equations, we get something that's more realistic, and that is manganese sulfide solid plus water liquid is going to be in equilibrium. So we just combine these two. The sulfide cancels out because the sulfide's a strong base. It's too strong to really be stable in water, and it's gone. And so the combined method works very well here. But the situation is we can't measure this. We can't measure this because sulfide won't exist. So the normal KSP, we're not going to be able to measure because immediately when the sulfide forms, it attacks water. And so the normal KSP, we don't have a number for that. Instead, what we have is we have the number for this. The number for this is going to be called KSP dagger, or KSP double dagger, or KSP asterisk, or KSPB. Where do I get KSPB from? KSPB comes from this. Every sulfide in this chart has a B. So if I look at manganese 2 sulfide, it has a B here, and it's MnS. And if I look at the KSP value, it's 3 times 10 minus 14. It's pretty insoluble here. That's it. If I look at mercury 2 sulfide, it has a B here. HCS is 2 times 10 minus 53. Sulfides are some of the most insoluble substances on this chart. In fact, this is the most insoluble substance on this chart. 2 times 10 minus 53. So what does the B refer to? So we have to go all the way down, 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 down until we get to B. And when we get to footnote B, for solubility equilibrium of the type metal sulfide, this is a 2+. Metal sulfide solid. What we're going to see is the KSP is equal to this equation. Metal sulfide solid plus water. The water, we need that for sulfide to attack. And this is going to make the metal 2+ plus HS minus plus OH minus. So our KSP equation is not the normal KSP equation. All sulfides will have this weird KSP equation. This one. So all sulfides have this type of equation. You know, it's the metal sulfide plus water yields metal cation plus HS minus plus OH minus. The 2+ sulfides will have this exact pattern. The 3+ sulfides will have a different splitting pattern. That is, the ratios will be a bit different. And so let's see if there are any 3+ sulfides. I don't think they put any 3+ sulfides here, even though those are highly insoluble, like iron 3 sulfide. They didn't put iron 3 sulfide. I guess they didn't want to make 2 footnotes, maybe. You know, because iron 3 sulfide would have a different splitting pattern like this. Show you. I guess that's not going to screw up. So we would get a different pattern here. Why is it disappearing? Okay, there it is. So if we had something like Fe2S3, you know, how many waters would I need for this? I'd need 3 waters. I'd have 3 sulfides. Each of those sulfides would attack water. And this would make 2 Fe3 plus 3 HS minus plus 3 hydroxides. And so this would be the KSPB equation for a 3+. You know, you see the ratios are a little different here. And so footnote B is only for the 2+ sulfides. And that's it. That's convenient because they omitted all the 3+ sulfides from the table. Even though the 3+ sulfides would be quite insoluble. All right, so that's one of the chemical properties of sulfide. Sulfide's a strong base. It hydrolyzes water completely, and so therefore, you know, we have to modify the KSP, and we end up with getting KSPB. So that's the first thing here, KSP. Looks weird. The next thing is we want to look at the pH and the solubility. Now, normally when we think about pH, we think just hydronium and hydroxide. And when we look at what we think is the KSP, it's sulfide, but sulfide's a strong base, we know, and therefore it's got to be pH dependent. But when we look at the combined here, that is the KSPB, then we see hydroxide there. So for sure, you know, pH is going to influence the solubility of hydroxide. I mean, not hydroxide, the sulfide. You know. And so hydroxide will change the solubility of the sulfide here. That is, the more hydroxide, the more it shifts to the left, the less soluble. The less hydroxide, the more it shifts to the right, and the more soluble it is. Well, rather than describing things in terms of hydroxide, we'd rather describe things in terms of pH. pH is hydronium, and so pH and the solubility of sulfides. The pH and the solubility of sulfides is a bit more tricky than the previous example because pH, hydronium, acid. Acid's going to attack the strongest base present. What's the strongest base present in my KSPB equation? It's going to be hydroxide. Hydroxide is the strongest base present. And so here, the hydronium will attack the strongest base present hydroxide. What does that form? It's going to form two waters. And I know this, I know this, because I think this is strong acid, strong base. Strong acid and strong base is going to give me a K that's very, very, very large. But when we do these combined ones, we want numbers. If we want numbers, I look at the reverse. Do you recognize the reverse of this? Reverse of this is two waters yields a hydronium and hydroxide. Well, that's Kw. And so this equation, second equation here, is just the reverse of Kw. So the K for that is 1 over Kw. And so rather than calling this very, very, very large, I just call it 1 over Kw, and I know what Kw is. Okay, thanks. And Kw is just 1 times 10 to the negative 14. All right, then I'm not done. I'm not done because hydroxide is the strongest base present, but you know what HS minus is? HS minus is also a base. HS minus is actually amphoteric. It's a stronger base than it is an acid when we look at this chart over here, but it's also a base that can be attacked by hydronium. So there are actually two bases. So once I knock out all the hydroxide, then I got to knock out the HS minus. And so the hydronium will attack the next strongest base after the hydroxide's gone. And that's going to form H2S in water. So this is strong acid plus a weak base. That should give us a K that's very, very large. However, I need a number. The number I'm going to get for this is this. If I look at the reverse equation, it's just H2S plus water. H2S plus water yields hydronium and conjugate base. Well, H2S plus water, that's acid plus water. Acid plus water is Ka. And so this is the reverse of the Ka equation for H2S. So I can actually get the numbers. Rather than calling this very, very, very large, I can get a number for this. But if I can get a number for this, why didn't I get a number before? For all the other reactions, because we didn't have to. What we're doing is we're just resetting, and then figuring out the equilibrium after that. So this is a way to reset. And so for the previous problems, we're still going to use very large, very, very large, and very, very, very large. But for these combined method ones, we're not going to do that. We're going to actually get a number for that. Does that make sense? And it's only for these that we're going to do it. For the previous ones, we aren't. So what I'm going to do is I'm going to combine this. When I combine these, I'm combining KSP, this B. The B does not mean base, unfortunately. That's why I like dagger or double dagger. This KSP is not the solubility in base solution like KSPA. KSPA is the solubility in acid solution. It's just their choice of footnote. And so don't get that mixed up. And I might start just calling it KSP double dagger. But I combine these three equations and I'm going to get MnS plus 2 hydronium here. This is going to yield Mn2 plus H2S plus 2H2O liquids. What species are missing from the combined equation? What species are missing are hydroxide. But is hydroxide stable in the presence of strong acid? No, so we expect the hydroxide to be consumed by the strong acid. So it's negligible. HS minus is the next strongest base. That's going to be consumed in the presence of strong acid. The strong acid is going to react completely with that. And so the species that are missing are not a big deal because you don't expect them to be present in the presence of strong acid. And so the combined method works here. There's no problem with it. And what we get for the net is going to be KSP attacked by acid. This is actually KSPB, or dagger. But when we look at our KSPA, it's going to equal our KSP for the sulfide divided by the Kw from step 2 divided by Ka for H2S from step 3. And then we can get the number for this. And then we can do an ice calculation here that I'm showing you here. So the number for this is KSP from the book is 3 times 10 to the negative 14. Kw we need to know is 1.0 times 10 to the negative 14, and Ka for H2S is 1.0 times 10 to the negative 7. And so just multiplying those out, we get 3 times 10 to the positive 7 here. 3 times 10 to the positive 7 means it's quite favorable to the right. When we do an ice calculation like this here, this would be an example here that we're talking about. We want to know the solubility of MnS at different pHs. And so, again, the pH could be the initial pH or the equilibrium pH, or it could be both, the initial and the equilibrium if it were buffered. If it were buffered, let's say I'm starting at pH 8.00. And so let's say, what is the solubility of MnS at pH 8.00? Well, pH 8.00 means that the hydronium ion concentration is 1.0 times 10 minus 8, just 2 sig figs. This is 2 sig figs here. If it were buffered, we start off at 1.0 times 10 minus 8, but as this reaction proceeds forward, this is going to go down, but the job of the buffer is to replenish that. And so even though, yes, this drops down, the buffer will make up for it. And so we start at 1.0 times 10 minus 8, that is pH 8, and we end at pH 8.00. Yeah. If the buffer is doing its job. Otherwise, if this were not buffered, then yeah, we're going to lose hydronium here as the reaction proceeds. Or if we're going reverse, we're going to gain hydronium. And so we have to read the question carefully. So this is, what is the solubility of MnS at pH 8.00? At pH means that it's the equilibrium here. At pH. That means maybe they had buffered it. And so we know what the final pH is. So we know the final pH. The final pH is going to be 1.0 times 10 to the minus 8. And then what we do is we look, at the solubility here. The solubility is, this will be plus X. But since X is the amount of MnS that's dissolving, it's all the 1 to 1 mole ratio, then we're going to call it S. This is the molar solubility. How many moles of MnS will dissolve? And so that's S and S here. And then we can just plug that into our equation. The KSPA, which is 3 times 10 to the positive 7 that we got here, is equal to the Mn2 plus times the H2S. Water is pure liquid, that's 1, divided by the hydronium squared. And so this is going to be S times S, divided by 1 times 10 to the negative 8 squared. It's not going to be 1 times 10 to the negative 8 minus X because, for some reason we have it buffered so that the X is replenished by the buffer. And then we can calculate the solubility. To calculate the solubility, it's actually quite low because this pH 8 is quite basic. Basic means this low hydronium concentration. And it gives us the solubility of 0.005477 molar. Then we can do a K check. We plug that back in to the K, and the K check comes out to 2.999 times 10 to the positive 7, which is good because the K is supposed to be 3 times 10 to the positive 7. Okay, it doesn't have to be like these two examples that we just looked at were hydroxide and sulfide. Those are strong bases, but it doesn't have to be a strong base to be pH dependent. What if it were a weak base? So for example, calcium sulfate. Calcium sulfate has calcium and sulfate as its ion product here. And if we think about calcium as a neutral, but sulfate is a weak base, and therefore pH should have an impact. But how does pH have an impact on sulfate? Because it's not hydroxide, it's not sulfide. Sulfide makes hydroxide. sulfate's gonna just partially hydrolyze water. So I guess I could do the Kb equation for that, but we're not gonna do the Kb equation for sulfate. In fact, what we're gonna do is we're gonna do a KSPA equation. If we do KSPA, it'll be more apparent how acid impacts this. And so the strongest acid here will be hydronium, and the strongest base will be, well, calcium's neutral, this is solid, so it's gonna be sulfate. Sulfate's gonna be the strongest base. So the strongest acid detects the strongest base, sulfate, and then what is it gonna make? It's gonna make hydrogen sulfate. Sulfate's gonna pluck a proton off, hydronium, make bisulfate and water. So this is strong acid plus weak base. Usually we say strong acid plus weak base is very, very large, but we need a number. So what we're gonna do is we're gonna look at the reverse equation here. When you look at the reverse equation, it's bisulfate plus water makes hydronium and conjugate base. So bisulfate, this is an acid, it's acting as an acid. And that's the Ka. Acid plus water is Ka. And so this is 1 over Ka for bisulfate. And then we can generate our KSPA equation. So we combine these two and we get our KSP equation, SPA equation, which is going to be these two multiplied, KSP divided by Ka for bisulfate here. And what this is going to say is, okay, when we look at the combined, we're missing sulfate, but when we have a strong acid present, you know, sulfate's going to react to form bisulfate. So we got bisulfate, which would be the major species when sulfate, there's acid present here. And so even though initially it looks like, it's kind of hard to figure out how hydroxide or hydronium changes the KSP equation, because hydroxide and hydronium aren't directly shown in the KSP equation. However, if we do a KSPA, then we can see how hydronium is going to impact this here. And using the KSPA equation, we can determine what the solubility is at different pHs more directly. And by changing the pH, you know, that's going to alter how much sulfate's present. You know, the more hydronium, the more sulfate that gets attacked, and the more this shifts to the right. And so the more hydronium, the more soluble it is. We could see that in the combined method here by Le Chatelier's principle. By Le Chatelier's principle here, we're removing sulfate. If we remove sulfate in reaction 2 here, then the equilibrium shifts to the right, solubility increases. However, if the hydronium decreases, you know, then we're increasing the sulfate because this equilibrium is going to shift to the left. If we increase the sulfate, the solubility decreases, you get precipitation. Or we can look at it in the combined equation. In the combined equation, the hydronium, you know, increasing or decreasing the hydronium, you know, increasing hydronium lowers the pH, so lowering the pH or raising the pH will have an impact on shifting the equilibrium to the left or to the right. If we shift it to the left, that's precipitation. If we shift it to the right, that's dissolution or dissolving. So we can end up dissolving some of these insolubles. So one way of trying to get to calcium sulfate's insoluble in water, but we could dissolve it in acid. That's one way. Could we get all of it to dissolve? Well, we could figure that out based on this. And so we can manipulate solubility with pH. Well, we can manipulate solubility with pH because of acid-base properties. You know, acid-base properties, sulfate is a base. Those are Bronsted acid-base properties. We can manipulate solubility, i.e. we can cause precipitation, or we could cause dissolution by altering the pH. But we can also do this using Lewis acid-base properties as well. That's another option. Or we could do this using what other types of properties do we have? So for example, here, you know, this isn't the only way to get MNS to dissolve, using acid. Using acid, we can get MNS to dissolve, increase the amount of acid, and get it to dissolve. Are there other ways of doing it? Yeah, there are other ways of getting it to dissolve, and that's taking advantage of other properties. So what are some other chemical properties that we could use to increase or decrease the concentrations, which would shift this one way or the other? Well, the other properties that we could use are metathesis and redox. And so one of the things that we could try to do is we could try to get an oxidizer in there. If we have an oxidizer in there, the oxidizer would attack HS minus. Sulfides are pretty good reducers. Something like that. That would alter it as well. And so sometimes we could use pH, that is the acid-base properties. Sometimes we could use redox. Sometimes we could use metathesis. Metathesis was we put another precipitating agent in there, a precipitating agent that's better than sulfide, although it's hard to find a precipitating agent better than sulfide. So when we set up a competition. But a good alternative to this is to use Lewis acid-base reactions to alter this. So when we're using Lewis acid-base, is this okay? I'm not writing this because I'm getting kind of late. Or you want me to write it down? So it's, are you guys following okay? It's already written down. Okay. So if I use Lewis acid-base reactions like this, then that's called KF for a specific type of Lewis acid-base. KF refers to formation of a complex. And KFs are generally big. KSPs are generally small because we're trying to dissolve insoluble salts. So I had written that up here. KSPs are generally small, like small numbers. Except these KSPAs, if I look at the KSP, it's quite small, but KSPA is quite big. Well, KFs are actually quite big too. And that KSPA was 10 to the positive 7. That's why I put positive there, because the KSP was 10 to the minus 14, which is quite small. And so this kind of flips the way we think about things, whether K is big or small. Well, KFs are big. Here. So here's a reaction. This is used in qualitative analysis for copper 2 ions. If I have copper 2 ions, it forms a very light blue solution. If I have ammonia in there, the ammonia attacks copper 2 and forms this is wrong. Fix that. It forms the tetraamine copper 2 ion. Normally we put square brackets here, but I'm not going to put square brackets because the square brackets gets all mixed up because I use square brackets for concentration here. So I'm not going to use square brackets on the complex here. And so this equation is the formation of a complex. Well, how do I know it gets attacked by 4 amines? Why not 2 amines? Why not 6 amines? Or maybe an odd number. Why not 5 amines? And so in order to predict how many amines will attack the copper 2, we would have to have a theoretical understanding of this. Unfortunately, we don't have a good theoretical understanding of it because it's not covered in this book. And so lacking that, we're just going to go to observational data. We're going to take a look at the observational data and look for patterns here. And so when we look at patterns like this, this is silver. Silver is being attacked by 2 cyanides. And so we call those cyano or cyanido ligands. And so this would be dicyanide, silver or argentate. What do we use? Let's name this. Argentate 1. So dicyanido-argentate 1, look at the Kf value for that. It's quite large. It's 5.6 times 10 to the 18. And the equation would be, for this particular one, would be 1 silver ion plus 2 cyanides yields the complex. That would be the Kf value for this. The formation of this complex, EDTA, this would be 6 coordinate because EDTA is a hexadentate ligand. There's something wrong with this though. Oh no, there's nothing wrong. What's the charge on EDTA? 4 minus. Silver is +1, so this is correct. This is a net charge. But when you look at this, which one's a better ligand? I would have thought EDTA would have been a better ligand, but when we look at the Kf values, which one has a bigger Kf? The cyanide. And so cyanide's an excellent ligand for silver. It's like better than EDTA. Ethylene diamine's pretty good. This is a bis-ethylene diamine. Ethylene diamine, this would be 4 coordinate. These would be 6 coordinate, this would be 2 coordinate. Amines would be monodentate, this is bidentate, 2 bidentate ligands. It's 10 to the 7. 2 amines there, 10 to the 7. Thiocyanate, 10 to the 10. Thiosulfate or thiosulfato, this would be thiocyanado, this would be thiosulfato or thiosulfate. 10 to the 13. Out of all these ligands, which one looks to be the best? It looks like cyanide. In fact, cyanide's an excellent ligand. Let's take a look at copper. Complexes over here. We have a number of copper complexes. This is going to be trichlorido cuprate 2. This would be 3 coordinate. It's 10 to the 5th. But look at this. This would be 4 coordinates. This is the tetracyano or tetracyanido, 10 to the 30th. It's an excellent ligand, right? Cyanide. And then the EDTA, 10 to the 18th. This is 6 coordinate. This is 2 ethylene diamines. This would be 4 coordinate, 10 to the 20th. We have 4 amines, 10 to the 13. 2 oxalatos, this would be 4 coordinate because oxalatos bidentate, 10 to the 8. Out of all these, which one do you think is the best ligand? Out of all these, the best ligand would be cyanide. In fact, cyanide's an excellent ligand. They use cyanide to leach out like silver, gold from mine tailings. Like if you drive up the 14 before Mojave, there's a gold mine there, or silver mine, silver or gold mine, or both. But there used to be, like, this is what I was told, I never verified this, but there used to be a leaching pit, and the leaching pit was filled with cyanide. And the leaching pit was just to get any kind of remnants of silver or gold out of the mine tailings there, you know. The problem with that was the winds would blow the cyanide, you know, laden water across the freeway, the 14 freeway. And so they had to cover it. There was some thing where there's some action taken and then they had to cover the pit, but it used to be an open, you know, leaching pit. Now it's kind of sealed to prevent that from happening. This was years ago on a geology field trip I went on. But anyway, cyanide's a good ligand, but cyanide's too toxic for us. So we're gonna pick something like amine. Amine's cheap and not terribly toxic. And so this is why we're gonna look at the amines here. And amines are pretty decent ligands. You know, the diamine silver is pretty good. You know, 10 to the 7, it's pretty good. So amine is very common, cheap, and a decent ligand. And so for copper, it's really quite good. 1.1 times 10 to the 13. Really quite good. And so what's going to happen is the amines are going to attack this, and the Kf is big. It's 1.1 times 10 to the 13. And so what's going to happen is it's going to form the complex. And so we have two copper-containing species. One, we have the free ion, which we call just copper 2+. And then we have the complex copper, the complex ion here. And so free ion and complex ion. And that means the total copper present is going to be the free plus the complex. And that's going to give us our total copper. So how much of the copper gets complex? Well, a lot of the copper must get complex because it's 1.1 times 10 to the 13. And so this question comes up as an example here. What percentage of the copper 2 that we start with here is complex in a solution containing, what is this? Ignore this here. This is probably just something that came down from above. In a solution containing 0.1 molar copper 2 and 3 molar ammonia. So these are the initial values. So what we're going to do is we're going to go here and plug in 0.1 molar initial copper 2 and 3 molar initial ammonia. And the amount of complex we're going to say is 0. And we're going to calculate how much complex is. But when K is big, I need to reset this. This K is quite big, so I got to reset this. I'm going to reset this to the right. If I reset this to the right, I use Y. So this is minus Y, minus 4Y. And then I'm going to figure out what the limiting reagent is. Which one of these two is the limiting reagent? Is it the copper 2 or the ammonia? The copper 2 is the limiting reagent here. And so I'm going to lose all of it. And so the copper 2 is going to go down to 0. And my ammonia, well, it's a 1-to-4 ratio. So if I lose 0.1 molar copper 2, I'm going to lose 0.4 molar ammonia because it's minus 4Y. And so 3 minus 0.4 gives me 2.6 molar. So I have a large excess of ammonia. And then I'm going to form the complex here. So I could say K is very large. I'd say K is very large if it shifts it completely to the right, just like we did before. But in this case, what we're going to do is we're going to just let it equilibrate now. So even though K is very large, I'm going to figure out what my equilibrium, I can't leave a 0 there. I'm going to figure out what my equilibrium concentrations are here. So it's going to shift back to the left. So it's going to go plus X, plus 4X, minus X. And therefore at equilibrium, I'm going to have 0 plus X gives me X. 2.6 plus 4X gives me 2.6 plus 4X molar. And 0.1 minus X is what I have for the complex. Now, if you don't reset this, then you're going to have trouble with the math in this chapter. Because if you don't reset this, then the math gets quite difficult. So we'll just plug this in. The complex is 0.1 minus X here, divided by the copper, which is just X over here, and then the ammonia, 2.6 plus 4X here, but it's raised to the 4th power. So I have this X times X to the 4th, which gives me X to the 5th. This is a 5th order polynomial. Our 5th order polynomial is easy to solve? No, so we need some trickery to solve this. And the trickery that we use to solve this is resetting it. Is if we reset it, then that means the simplifying assumption is more likely to work. And so we try the simplifying assumption. We just say that, going backwards, the change should be small. Going forward, the change is huge, but going backwards, the change should be small. Therefore, 0.1 minus X is just 0.1. And 2.6 plus 4X is just 2.6. And so that greatly simplifies the math. And so that means X is equal to 0.1 divided by 1.1 times 10 to the 13 divided by 2.6 to the 4th, which gives me an X value of 1.989 times 10 to the minus 16. So the change was 10 to the minus 16, and my initial is 10 to the minus 1 here. It's negligible change. And the change is going to be, this is 2. 2 times 4 is 8. 8 times 10 to the minus 16. 8 times 10 to the minus 16 versus 10 to the 0 is negligible. And so the percent change is extremely small. Therefore, the simplifying assumption is valid. If the simplifying assumption failed, then you're in for a headache because you'll have to solve it using the method of successive approximations. But fortunately, we don't have to do that. We'll go back here, we'll plug in, so x is 1.989 times 10 to the minus 16 here. And then 2.6 plus 2 times 10 to the minus 16 is the 2 times 10 to the minus 16 is way out here. Your calculator can't even do this. And so it's just going to come out at 2.6. And then 0.1 minus 10 to the minus 16 is going to be 0.9999999, whatever, 0.099999, whatever. And so that's just pretty much 0.1. And then we do a k-check. The k-check is going to be 0.1 divided by 1.989 times 10 to the minus 16 divided by 2.6 to the fourth, and it comes right on. Our k value comes out to 1.10000 times 10 to the 13, which is 1.1 times 10 to the 13. So the k checks out. But I'm not asking for the equilibrium. I did the equilibrium concentration so I could do the k check. What I'm asking for in this particular problem is what percentage of the copper is complex. So I have a total amount of 0.1 molar. How much was complex? How much is free? So when I do this, I have to go back to the original initial, not the reset initial. When I look at the original initial, I start off with 0.1, and then I only have this much remaining, 1.989 times 10 to the minus 16 molar remaining. And so this is like, you know, the percent reaction or whatever. What we're going to do is we're going to calculate the percent remaining first. So the percent copper 2 that remains free is 1.989 times 10 to the minus 16 remains free out of the original total of 0.1 times 100% gives me 1.989 times 10 to the minus 13% remaining. So the percent of free, that's the copper 2 remaining, plus the percent complex has to add up to 100%. And so the percent copper 2 that was complex, should write that here, is going to be 100% minus the percent remaining. Well, the percent remaining, if you punch this in your calculator, it's going to come out to 0%, 100%. But I didn't want it to come out to 100%, so I just did it by hand. And so it's going to be 99.99. We're going to have 12 nines after the decimal. So that should be 12 nines, and then an 8, etc. Or about 8, because this is about 1.98. Something like that. 989, actually, something like this. So close to about 100%. I mean, if we have the cutoff at 99.9, then this is essentially completely complex. It's not literally completely complex, because if it were literally completely complex, it'd go down to 0. It didn't go down to 0. This would be complete 100%. We just had slightly less than 100%. There. All right, so that means that even though ammonia didn't have the highest KF, boy, is it effective at complexing, you know? It really ate up all the copper too. Do you see that? And so the percent reaction here is huge here for this. So what this means is this. Just gotta look this way. And so let's look at something called KSPF. KSPF is combining KSP and KF. And so doing that, let's take a look at a example here. An example here is, think of an insoluble copper salt. An insoluble copper salt would be something like copper carbonate. And so there are different ways we can tackle this. For example, we could do a KSPA. Carbonate's a base, and so that could be attacked by acid. We have KSPA. Or we could do a KSPF. By doing KSPA or KSPF, we can increase or decrease the solubility. And so, for example, here, if I have copper 2 carbonate solid, and I look at the KSP equation, that's going to form copper 2 plus carbonate. This is KSPF, what we're looking at. So if I go the acid route, what will hydronium react with here? Hydronium will react with carbonate. Will form bicarbonate and water. So I could use pH. By changing the pH, that's going to change the amount of hydronium, which is going to change the amount of carbonate. And by changing the amount of carbonate, that's going to shift this to the right, increasing solubility, or shift it to the left, decreasing solubility. So we can use pH to alter the solubility here. This would be KSPA. Or I could do a KSPF. Except I'm not going to use hydronium. I'm going to use the Lewis base ammonia. Ammonia is an excellent Lewis base. And ammonia is going to attack what? The copper. It's 4 ammonias. How do I know it's 4? Because I just look it up in the table. It's just from observation. And that's going to form the amine complex here. So if I go the KSPA route, I'm altering the carbonate concentration. If I go the KSPF route, I'm altering the copper 2 concentration. Either of those will work for changing this, so I could do it whatever way I want. But anyway, I'm out of time here, so we'll talk more about the KSPF next time.